From the outside, an abandoned luxury hotel in Dubai might look perfectly frozen in time. Walk through the empty lobby, past the dry water stains, and stand beside an apparently normal reinforced concrete column. The physical threat to this building does not start on the surface. Several centimeters inside that column, moisture may be interacting with the reinforcing steel. Localized corrosion can begin, rust products slowly accumulate, and pressure builds around the rebar until an internal fracture starts moving outward. Eventually, the concrete cover cracks and breaks away. An abandoned hotel does not stop aging just because the guests disappear. But why does leaving a building completely empty make a hidden defect so much harder to stop? The Renaissance Dubai Motor City and Marriott Courtyard projects provide a historical example of how development can suddenly pause. The two hospitality projects were originally planned to contain nearly 600 rooms combined, and reports indicated they reached roughly 75% completion before construction stalled. They offer a useful way to understand what happens when a massive concrete structure simply sits waiting. The site becomes silent, but the environment remains active. Temperatures rise and fall every day, forcing materials to expand and contract. Humidity changes moisture levels in the air. Water can still enter through unfinished roofs, open shafts, exposed basements, or weak waterproofing. Sealants, gaskets, and temporary protection systems continue facing ultraviolet exposure and thermal fatigue. Without active climate control, interior spaces can absorb and retain intense heat. An unfinished facade may also leave joints exposed to coastal air carrying salts. The contradiction is simple. The building stopped. The environment did not. To understand why an empty structure is so deeply vulnerable, you have to look at how reinforced concrete actually fails. The concrete itself does not simply rot away from exposure to the outside air like a piece of untreated wood. The primary deterioration mechanism usually begins around the steel rebar embedded deep inside the structural core. Under the right environmental conditions, a localized chemical reaction starts near the delicate microscopic interface between the steel and the surrounding concrete. When that steel begins to actively corrode, the resulting rust products take up significantly more physical volume than the original solid metal. This expansion can be 3 to 6 times the volume of the original steel, depending on the specific oxidation process taking place. This massive volumetric expansion creates immense localized tensile pressure, pushing outward against the surrounding concrete structure. Concrete is famously strong under compression, allowing it to hold up massive skyscrapers, but it is notoriously weak under tension. The material can only handle so much internal stress before it fractures, simply to relieve that immense pressure. An internal microcrack forms first, moving silently toward the exterior surface over a period of many months or even years. Eventually, that internal pressure reaches the surface, causing a visible crack or forcing entire chunks of heavy concrete to spall off completely. This specific chain of events means a severe physical failure has already happened by the time you can actually see the damage. But this raises an immediate structural engineering question. How do moisture and aggressive chemicals reach that steel in the first place when it is buried inside several centimeters of solid rock? Concrete looks like an impenetrable wall, but it is not perfectly sealed against the natural elements. At a microscopic level, it contains complex pore networks and capillary channels that can allow moisture and dissolved ions to move slowly through the material. In a coastal desert environment like Dubai, the air carries heavy atmospheric chlorides and humidity directly from the Arabian Gulf. When that moisture lands on a building facade, high evaporation rates quickly leave the concentrated salt deposits behind on the surface. But the physical threat does not usually require a slow, difficult path through the incredibly dense center of a perfectly poured column. It only needs a single vulnerable route toward the internal steel reinforcement. That route could easily be a poorly sealed roof joint, a tiny gap in the exterior facade, or a compromised thermal expansion joint. It could be a failed construction joint near a wet basement zone where the local groundwater fluctuates throughout the year. A minor waterproofing defect on an exposed concrete pool deck can provide all the access required for standing water to penetrate. Dissolved chlorides or moisture move through these weak points depending on the specific concrete mix design and the building's exposure history. The moisture slowly travels inward until it disrupts the highly alkaline environment that normally protects the internal steel. The concrete initially provides a naturally high pH environment, which forms a thin, protective passive oxide layer directly over the surface of the rebar. However, when chloride ions successfully penetrate the concrete cover and reach the steel, they act as a catalyst to break down this vital protective layer. Once that passive protection is completely destroyed, the localized corrosion process is cleared to begin. When growing internal pressure finally breaks the surface, the structural problem changes. The first visible crack is not merely a cosmetic symptom, it changes the future exposure of that concrete element by creating a much easier route toward the reinforcement. Moisture, oxygen, and chlorides no longer have to move only through microscopic pores. They can penetrate through the crack whenever the surface becomes wet from condensation, leakage, wash water, or rain. That can accelerate corrosion at the damaged area. More corrosion creates more expansive products. More expansion can widen the crack and extend damage along the reinforcing bar, exposing neighboring sections of steel to the same environment. The damage begins creating conditions that make further damage easier. That feedback loop is the real meaning of the hidden corrosion trap. And once it begins, it does not pause simply because the property is waiting for a new owner or developer. An empty building does not just lose its paying guests and daily staff members. It completely loses its accidental human sensors. In a fully operating hotel, a guest notices a water stain spreading across a ceiling and complains to the front desk. A cleaner reports a damp patch near a window frame while preparing a room for the next visitor. A facility technician hears an abnormal pump vibration in the mechanical room, and a maintenance crew quickly opens a work order for a failed seal. These daily human interactions act as a highly effective active monitoring network for the entire building envelope. If a leaking condensation line dropped water onto your ceiling tonight, how long would you leave it there before calling for help? Now imagine that exact same room had been entirely empty, locked, and completely unmonitored for 3 long years. This answers the crucial question of why an abandoned building is so physically vulnerable to environmental decay. Leaving a massive structure empty does not magically cause active corrosion to appear out of thin air. Vacancy becomes dangerous because it removes the early warning system that catches moisture intrusion before it ever reaches the structural core. When daily visual inspection and routine active maintenance disappear, minor mechanical defects can remain undiscovered while the environment continues to endlessly test the building envelope. A tiny problem that could have been solved with a $50 tube of commercial sealant eventually becomes an incredibly expensive structural repair. If hidden internal deterioration eventually causes concrete to crack, the natural instinct is to assume building inspectors can simply look for those cracks. But relying entirely on visual inspection offers a highly dangerous false sense of relief. A perfectly clean exterior facade can hide severe localized corrosion that is already generating massive internal pressure. By the time you can physically see the fracture on the surface, the underlying deterioration process has already been progressing in the dark for a very long time. This is exactly why structural engineers must use specialized forensic tools to properly evaluate older or abandoned concrete structures. They utilize cover meters to accurately locate the exact depth of the rebar beneath the surface. They perform half-cell potential testing to map distinct areas of active corrosion activity that remain completely invisible to the naked eye. They literally drag heavy metal chains across concrete decks, or use specific inspection hammers to manually strike the columns. When the hammer suddenly produces a dull, hollow sound, it strongly indicates that the concrete has already delaminated internally, even if the surface looks completely intact. Human eyes alone simply cannot tell the entire structural story. Sometimes the beautiful facade is where the hidden story finally becomes obvious, not where the actual deterioration begins. This dangerous delay between internal damage and visible surface evidence is exactly why Dubai made a fundamental change to its building rules in 2026. Dubai Law Number 3 of 2026 on the quality and safety of buildings established an emirate-wide framework for building quality, condition assessment, inspection, certification, and maintenance responsibilities. The law does not mean Dubai is experiencing a city-wide structural crisis. It points to a different reality. A rapidly built city eventually has to become a rapidly maintained city. For decades, Dubai became famous for turning desert plots into architectural landmarks at extraordinary speed. But once those structures exist, the engineering challenge changes. Constructing a tower demands enormous capital once. Keeping it safe demands attention for decades. As the city's building stock matures, inspection, maintenance, repair, documentation, and asset management become permanent obligations rather than occasional afterthoughts. That transition is less spectacular than launching another megaproject, but it may be just as important. The question is no longer only how quickly Dubai can build, it is how effectively it can monitor and preserve everything already standing. This hidden deterioration is not just a theoretical threat designed to make an empty hotel column sound frightening on the internet. The physical mechanisms driving this hidden damage are heavily documented and verified in real-world structural engineering across the globe. According to extensive reinforced concrete corrosion research by the Federal Highway Administration, chlorides can successfully disrupt the vital passive condition of internal steel. Their verified research confirms that this allows expanding corrosion products to form near the interface, eventually contributing to severe concrete cracking and dangerous spalling. The National Institute of Standards and Technology detailed very similar deterioration mechanisms in Technical Note 2377, published in 2026. That specialized engineering document explains that corrosion initiation relies heavily on moisture, oxygen availability, specific exposure history, and the exact steel-to-concrete interface conditions. It clearly emphasizes that a single vulnerable route through the concrete cover is absolutely all that is needed to trigger the devastating depassivation process. What looked like a microscopic chemical reaction earlier in this story is actually a globally recognized, highly destructive failure mode for reinforced concrete. It is a primary reason why coastal infrastructure everywhere in the world requires continuous funding for heavy rehabilitation. The simple abandonment of a building merely accelerates the timeline by completely removing the maintenance crews that usually fight this exact physical battle every day. Once corrosion-related damage reaches the surface, a cosmetic repair can become a dangerous distraction. A maintenance crew may patch a crack, repaint the area, or apply sealant so the column looks normal again. But if the steel beneath is still corroding and the original moisture route remains open, the underlying process can continue behind the repair. Cracking may return, delamination can spread. Eventually, reinforcement may become directly exposed to the environment. That does not mean every crack is a structural emergency. Large buildings settle, concrete shrinks, materials expand and contract with temperature. Some hairline cracks are superficial. But cracking associated with reinforcement corrosion is different because the visible defect is only the surface expression of a deeper material problem. At that point, the real question is no longer, how do we hide this crack? It is, why did this crack form, and what is still happening behind it? This leads to one of the biggest misconceptions about aging infrastructure. When people hear the word collapse, they imagine a dramatic moment, a tower falling into the street in a cloud of dust. Real structural decline is usually slower and less cinematic. It may begin with a small leak or defect that escapes notice. That creates repeated localized repairs. Over time, cracking and spalling may worsen around important structural elements. Access to affected areas can be restricted because of falling debris. Engineers may have to remove deteriorated concrete, treat exposed reinforcement, and install strengthening systems. A city does not need skyscrapers falling into the street before aging buildings become a serious engineering and financial problem. The first collapse is often less dramatic. It is the collapse of easy maintenance, then the collapse of low-cost repair, and eventually, If deterioration becomes severe enough, the collapse of the asset's economic logic long before the building itself collapses. When structural decline finally reaches this advanced stage of intervention, time does not just change the physical severity of the damage. Time completely changes the entire scale, complexity, and massive cost of the required engineering solution. Early detection of a minor moisture leak might mean a strictly targeted inspection zone, local ladder access, and a relatively small repair bill for a single waterproofing membrane. But late discovery transforms a simple daily maintenance task into a massive, highly disruptive structural rehabilitation project. It requires erecting huge exterior scaffolding systems and executing precise hydro-demolition to meticulously blast away the bad concrete using ultra-high-pressure water jets. This specialized technique removes the failing material without causing microfractures in the healthy concrete or severely damaging the remaining internal steel. Engineers must then inspect every single piece of exposed rebar to calculate the exact percentage of section loss. If the steel has lost too much of its original diameter, entirely new reinforcement must be physically spliced or carefully welded into the existing structural cage. Finally, they might need to install an active galvanic cathodic protection system to forcefully halt any remaining active corrosion. A hotel operator facing this nightmare might be forced into a partial building closure, effectively destroying the asset's economic viability for the entire tourist season. Now shift your perspective from the original builder to a future property buyer, an institutional investor, or a developer purchasing a dormant asset at a perceived massive discount. You do not only inherit the massive concrete structure, the high land value, and the striking architectural design, you fully inherit every single drop of water, every intense thermal cycle, and every tiny chemical reaction that happened to the material while nobody was looking. This deeply complex reality leads to the real long-term engineering trap for the entire region, stretching far beyond one abandoned hotel. The genuine threat is not that every single massive building in Dubai is currently actively corroding or structurally failing at this very moment. The universal truth of global urban development is that every single newly built structure eventually transitions from a glamorous construction challenge into an exhausting, endless maintenance challenge. Dubai built its modern global reputation by turning empty desert ground into a staggering skyline of architectural achievements. This explosive property development occurred in an incredibly compressed time frame, completely transforming the region's urban footprint faster than almost anywhere else on Earth. But because so much of the city's heavy concrete infrastructure was built in the exact same rapid 20-year window, all of those existing structures now age together. They will inevitably enter their second, far more expensive life cycle phase at roughly the exact same time in the near future. That upcoming story is entirely defined by constant forensic inspection, proactive aging management, highly localized concrete repair, and endless material renewal. Walk through some of the older urban districts today, and you will clearly see the physical contradiction of a rapidly maturing city. A brand new luxury tower rises on one block, while engineers silently test the concrete facade of an older high-rise directly across the street. A massive construction crane swings through the sky, while an equally massive repair scaffold stands nearby. The core systemic question is whether a rapidly growing city can endlessly build exciting new icons while simultaneously carrying the massive, growing maintenance responsibilities of everything already standing. The heavy maintenance burden grows silently, and it never truly stops. Return to the abandoned luxury hotel one last time. Look past the dust, the dry water stains, and the desert sunlight cutting through an empty corridor. A structural engineer moves a flashlight across a silent concrete column, then strikes the surface with an inspection hammer. A dull, hollow sound echoes down the hallway. The most unsettling years in a building's life are not necessarily the dramatic moments when concrete finally breaks away. The most dangerous years can be the quiet ones. The years when moisture keeps finding a path, corrosion progresses out of sight, and the building still looks calm enough that nobody realizes where to look. Now return to the perfectly normal concrete column from the beginning. the entire chain becomes clear. Moisture and dissolved chlorides find a vulnerable route through joints, cracks, porous concrete, or failed waterproofing. They reach the embedded steel and can disrupt its passive protection. Corrosion begins. Expansive corrosion products build pressure around the reinforcement. Cracks form. Those cracks create easier pathways for more moisture and salts, accelerating the cycle. The frightening part is not that this guarantees collapse. It does not. The frightening part is how long the process can remain almost invisible. Dubai became famous for building structures that once looked impossible, and doing it at remarkable speed. Its next engineering challenge is slower, less glamorous, and harder to photograph. Keeping thousands of existing buildings healthy as they age, because the visible crack on a luxury facade is not necessarily where deterioration begins. It is where the hidden problem finally becomes impossible to ignore. This video is produced for educational and documentary purposes to explain deterioration mechanisms in reinforced concrete. It does not claim that any specific abandoned hotel or operating structure in Dubai is currently facing imminent structural collapse. The engineering principles discussed are based on established materials science and structural research and should not replace a professional structural assessment or forensic inspection. So here is the question. Would you rather buy a slightly older building with a complete maintenance history or a beautiful newer property that spent its first few years sitting almost entirely empty? Tell me why in the comments. And if you want to understand the hidden engineering forces quietly shaping modern cities, subscribe and join the next investigation.